All right, so this problem says a conductor carries a current that is decreasing exponentially with time. So here is the current as a function of time. And you'll see that this is the current when you discharge a capacitor. You'll see this in the next chapter. So let me draw a circuit to show you. So for instance, okay, these are resistors. This is a capacitor, this is a battery. And for instance, this is a defibrillator circuit like this. This is the flash camera circuit is like this. So when you close the switch, the capacitor gets charged. And once the capacitor is charged, you can open the switch. And now you're ready to take a picture or you're ready to restart a heart. This can be a heart, this can be a flash camera. So when you're ready to take a picture, you close the switch and the energy stored in the capacitor discharges through the bulb. And the current that flows through this load decreases exponentially like that. Okay? So that, so you'll learn all of that next chapter. Okay, so a conductor carries a current that is decreasing exponentially with time. The current is modeled as that. This tau is the time constant. So after that time, the current has fallen to about 35% its initial value. Okay, so the time constant, you'll hear this expression time constant all the time in circuits. That's the time scale on which things change, okay, significantly. Okay, so tau is a time constant. Okay, I naught, the initial current is 3 amps, and time constant is half a second, is the time constant. How much charge flows through the conductor between t equal to 0 seconds and t equal to 3 tau? Okay. Now, if you look at your notes, dq by dt, current is the rate at which charge is flowing at any location. Okay. And so you have an equation, and you hit this guy with a hammer, you have to hit this guy with a hammer. Okay, so what we'll do is we'll integrate both sides, and the limits of integration will be 0 to 3 tau. An integral is an antiderivative, so this is just qt 0 to 3 tau. Okay, and what this is q at 3 tau minus q at 0. What this is telling you is how much charge has flown across a point at time 0, and what is the total charge that has flown across at time 3 tau. Okay, so if you're closing the switch at 0, so this will be 0. So, all right. So anyway, the charge that flows through in 3 tau time. Okay, and this, the left-hand side is integral of I naught e to the power minus t over tau. And I naught is a constant. Integral of minus t over tau is 0 to 3 tau. And so this becomes minus I naught times tau e to the minus 3 tau by tau minus E01. So that's the charge, net charge that has flown between these two times. Okay. Now this guy is e to the power of minus 3. This is smaller than him, so we'll absorb a minus sign. So I naught times tau is 1 minus e to. Okay. So now, so that's what we want to calculate. Amps is coulombs per second. Amps is coulombs per second, and this is, as units of time, 0.5 seconds. So this will be coulombs, and this is just a number. Okay. And so you can calculate that. So 1.3 coulombs of charge has flown through in that time scale. Okay. That's what that is. All right, so this problem says the quantity of charge through a conductor is modeled as that Q is 4t to the power 4. See, each term has to be coulombs, so this term is coulombs per second to the 4 because you have a t to the power 4 there. Okay? Minus 1t plus 6 millicoulombs. Okay, so see, each of these are in coulombs, that's in millicoulombs, so that you should really write that as 0.006 coulombs. So here is qt is 4t to the power 4 minus t plus 0.006, and that's coulombs. Okay. They ask you, what is the current at time t equal to 3 seconds? Current at any time is the rate at which charge is flowing. Okay, so it's 16 t cubed minus 1, and that'll be coulombs per second, which is amperes. And you want to find it at 3 seconds. So 16 times 3 cubed minus 1. So at 3 seconds, you have 431 amps flowing. That's a large current. That's roughly the current flowing through 10 washing machines. So you can see that current flowing in a laundromat, for instance, in a large laundromat. Okay, so this says consider a wire of circular cross-section with a radius of 3 millimeters. So it's a fairly thick wire, about that thick. The magnitude of the current density is CR squared. Okay, so let's say here's the cross section of the wire, and the current is coming out of the sheet, let's say. And what they're telling you is, okay, so if you're R distance away, the current density at this location, so in this little ring, the current density is CR squared. Okay. So the current through this ring is the density times the area of this ring. So the current flowing at distance R is the density times d area. What is the area of this ring? So this is the width of the ring is dr. What is the area of that ring? It's 2 pi r, the circumference of the circle. That's the length times the width, which is dr. Okay. So 2 pi r times dr. All right. What do they ask you? What is the current through the inner section of the wire from r equal to 0 to 0.5 r? Okay. So r is the radius of the circle, and they want you to find the current through the inner half of the wire. So the total current is IR. Yep. Yeah, so that's the current through this ring, and so you're adding all the rings, and you're going from 0 to R. Okay. dr 0 to 0.5 R. And so it's 0.5 R. Two pi C R to the power 4 by 4, 0 to 0.5 R. 2 pi C by 4, 0.5 R to the power 4. All right. So the current through the inner half is 2 pi over 4. C is 5 times 10 to the 6. Okay. And again, these are all, okay, I'll write down the units. Amps, meters to the power 4 times 0.5 to the 4, and R, the radius of the, is 3 millimeters. Okay, the meter to the power 4 cancels with that, so and you'll get amperes. Okay, let's take care of powers of 10. That's 10 to the minus 12, and then you get 10 to the minus 6. So, and then we'll absorb 1. That's 10 to the minus 1, and to the 4, 10 to the minus 4, and 10 to the minus 6 is 10 to the minus 10. Amperes, 2 pi by 4 into 5 to the power 4 into 3 to the power 4. Okay. Okay, so this works out to 39.8 into 10 to the minus 6 amps. Okay, so that's the current. And what is that? That's the current flowing in this inner half. Okay. All right. Will the current flowing in this part of the wire be more or than this or less? Okay, so see the density is increasing with R. So there's more and more current flowing here, and the area is greater. The current will be much larger there, okay? But anyway, maybe you guys should go at home and try that. Try the current flowing from here in this half. And what would you do? You take the integral from 0.5 R to R, okay? And calculate the ratio of the currents. Okay, I bet you it'll be greater than 10. The current supplied to an air conditioner unit is 4 amps. The air conditioner is wired using a 10 gauge diameter, 2.588 millimeter wire. The charge density is that. So in that wire material, what this means is every meter cube of that metal. So here's a meter cube. This thing is a meter cube. A meter cube of that metal will have that many free electrons, 10 to the 29 free electrons. Avogadro's number is 10 to the 24. So 100,000 moles of free electrons. Yeah. Find the magnitude of the current density and the drift velocity. So the current is NQ, the charge, times drift velocity times area, and the current density is I over area, which is NE drift velocity. So they give us the current, and we have the area of cross section. Oh, well, they give us the current. What is it? Find the magnitude of the current density. Okay, the current density is this. No, current density is current divided by area. We have those two. So let's find that first. Current is area. Area is the area of cross section of the wire is pi r square. Okay. So current is 4 amps. Pi r is diameter, that's so 1.294 millimeters. Okay. So that is the current density. Okay. And so that squared is -6. When it comes to the top, it becomes +6. So the current density is 4 times 10 to the 6 amp per meter square over pi times 1.294 square. So that is the current density. What this means is in the air conditioning wire, so here's a meter square. If the wire were this thick, the current flowing through that wire would be 3/4 of a million amps. That's what that means. Yep. And all you wanted was 4 amps, so you had the wire correspondingly, the thickness of the wire was such that. Okay, that's the current density. And part B, they want you to find the drift velocity. What is the drift velocity?
The slow velocity that electrons are moving along, because they're mostly staying in place, but they will slowly drift, right?
And when will they drift?
When the current's actually flowing through it.
Yeah, so if you establish an electric field in the wire, the electrons will drift, okay? And these drift velocities are of the order of millimeters per second. This drift velocity is on top of the random velocity that they're undergoing. You guys remember the random velocity? Anybody?
Quick.
Really quick, yeah. How quick? 1,000 kilometers a second. They go from here to Atlanta in 1 second. On top of that, there's this tiny drift velocity. Okay. All right. So that's what we're going to calculate. The drift velocity is the current density. Okay. E is the charge of the electron. Okay. So current density was 0.76 times 10 to the 6 amp per meter square. N was 8.48. Per meter cube. And anybody remember the charge of the electron? Okay, 10 to the minus 19 coulomb. Okay, so let's take your powers of 10. This is 10 to the 9, and then you get 10 to the minus 3. 10 to the minus 3 meters per second. Okay, and that's good because that's a millimeter. 0.76 over 8.48 into 1.6. Okay. Hmm. 0.06 into 10 to the minus 3 millimeters per second. Okay, so that's a millimeters. It's 0.06 millimeters a second. Okay. So you see a 10 gauge wire has a diameter of that. A 0 gauge wire has a diameter of that. So as the gauge number decreases, the wire gets thicker. The thicker the wire, the lower its resistance. Assuming it's made of the same material. Okay. The diameter of a 0 gauge copper wire is 8.252 millimeters. Find the resistance of a 1 kilometer length of such wire used for power transmission. Okay. Resistance is resistivity times length divided by area of cross section. Longer the wire, greater the resistance, greater the area of cross section, lower the resistance. Okay, and this is a property of the material. So let's look that up for copper. Um, Okay. Here's resistivity for copper, 1.7 times 10 to the minus 8 ohm meter are the units. The length is 1 kilometers, 10 to the 3 meters, and area is pi r square. R is half of this, 4.126. 4.126 millimeters square. All right, let's take your powers of 10. That's 10 minus 6. You get 10 minus 2, and then 10. So, and we'll multiply that 10 with 1.7. So 17 divided by pi into 4.126 square. And the units will be meter square, meter square cancel. So ohms is the units for resistance. So 1 kilometer copper wire has a resistance of 0.3 ohms. Okay. 1 kilometer zero gauge copper wire. A kilometer is from here to Embry-Riddle. A resistor is connected in series with a power supply of 20 volts. The current measured is 0.5 amps. What is the resistance of the resistor? Okay, so here is the circuit. There's the voltage, current, resistance. And Mr. Ohms tells you that the current in the circuit is the voltage. The current in the resistor is the voltage across the resistor times the resistance. Okay. So this is 20 volts divided by R equal to 5.5 amps. So the resistance is 20 volts, and volts over amps is ohms. So this is 40 ohms. This problem says, what is the maximum voltage that can be applied to a 10 kilo ohm resistor rated at 1/4 of a watt? Okay, so if you apply a greater voltage, there will be a greater current in the resistor, and the resistor will burn. Okay. If you check your notes, you'll see that the power dissipated in a resistor is the voltage times the current across the resistor. It's V squared divided by R, or I squared times R. Okay, so you can use one of those three formulas. Well, they give you the resistance, and you want to find the maximum voltage. So this is the formula we'll use. Power equal to V squared over R. So V is square root of power. So maximum power equal to, okay, V Vmax, maximum power is 0.25 watts, and resistance is 10 kilo ohms, which is 10 to the power 4 ohms. And square root of watts times ohms is volts. So you get 0.5 into 10 to the 2 volts, 50 volts. So maximum voltage you can apply to that resistor is 50 volts. You apply 51 volts, the current is too large and it'll burn, okay? And so what do you do to protect from your toaster burning and stuff like that? Or the wire inside behind the wall from burning? What do? You break down your walls and repair the wire? You have fuses, yep. That's what the fuses are for. So you don't have to break your walls down every time. A heater is being designed that uses a coil of 14 gauge nichrome wire to generate 300 watts using a voltage of 110 volts. How long should the engineer make the wire? Okay, power is voltage squared divided by R. So the resistance you want is voltage squared divided by power is 110 volts squared divided by 300 watts. Okay, and so the resistance of the wire you want is 40.3 ohms. Now the resistance of a wire is the resistivity times the length divided by area. All right, let's find the diameter of the 14 gauge wire. What is the diameter of a 14 gauge wire? The diameter of a 14 gauge wire in centimeters. Okay. So the diameter is 0.1628 centimeters. The radius is 0.0814 centimeters. Okay. All right, so the length of the wire you need is resistance times area divided by rho. Resistance is 40.3 ohms. Area is pi r square, 0.814 into 10 minus 3 meters square. And the resistivity of nichrome is 1.5 times 10 to the minus 6. Okay, the ohms cancel. There's a meter square and one of the meters cancel, so you'll get meters. Okay, this is 10 to the minus 6, which cancels that. So what you get is 40.3 into pi into 0.814 square divided by 1.5 meters. So half a football field length, actually a little more, 2/3 of a football field length. That's how long the wire needs to be. And you know, you got to wind that into a little heater element. Yeah. And as you're winding them, you got to make sure it's insulated too. So alternate to CFL bulbs and incandescent bulbs. So, well, these are CFL are compact fluorescent light bulbs. These are fluorescent light bulbs. The incandescent are those yellow ones. Those incandescent bulbs, they're about 5% efficient. What does that mean?
Other 95% goes to heat.
Yeah. So of the electrical energy supplied, only 5% is converted to light. These guys are about 40% efficient. LEDs are about 95% efficient. All right, so in the world today, there are about okay, so here, roughly about 10,000 coal power plants, large coal power plants. 15% of the electricity produced is used for lighting. So if you replace every one of those bulbs with an LED bulb, all that electricity for lighting will essentially go to zero. You can close down 1,500 coal power plants, large. Okay. All right, so a 100-watt incandescent bulb can be replaced by a 16-watt LED bulb. Okay, so you see it's both produce 1,600 lumens of light. Assuming the cost of electricity is 10 cents per kilowatt hour, how much does it cost to run the bulb for 1 year if it runs for 4 hours a day? Okay. So to run an incandescent bulb, we'll calculate that. So per kilowatt hour, what we're going to do is we're going to run it 4 hours a day, 4 hours, 365 days, And we're going to run the 100-watt bulb. 100 watt is 0.1 kilowatt, right? So here you have kilowatt hour, the day cancels. You have a kilowatt hour, that cancels with that. So you just get the cost. So that's how much it costs you to run, keep that 100-watt bulb lit 4 hours a day. $14.60. Okay, so if you do the LED bulb, what would be the cost? So the LED bulb, it's 16 watts, so it's 0.16 times that. So 0.16 times that. Okay. Point. So to keep the LED bulb lit, it costs you $2.34. Okay, why would you want to do a calculation like this?
Find out if your light bulb's saving you money or not.
What's that?
So you're gonna find out that your LED light bulb's gonna be
Right.
cheaper.
So as an engineer, you have to do this, and all the big cities, about 10 years ago, LED bulbs were expensive. And this is the calculation that was done, and all big cities like Los Angeles and all are saving $15 million a year on street lighting by switching to LEDs. All right, guys, that's it for today.